This means, and this is important, that for what it is related to us, let's see, for example, the alloy here, number 4. Well, for us, in this case, with this alloy, with a nitinol composition 4951 atomic of the two elements, but with a specified post-treatment, we can achieve the formation of 100% of martensite, if we want to use the same words, when we are going to lower the temperature. But for us, the lowest temperature is room temperature, that is 24 Celsius. And then we can achieve the full formation of again of austenite from the formed martensite when we achieve the high temperature value, which is, in this case, for us, around 70 Celsius. That is, they are temperature value which can be easily managed in an industrial way, and thus we can have, and we have available, nitinol materials which can be processed by using the shape memory behavior they can exhibit without any particular difficulties. Now come back to the modeling, okay, and start to discuss about modeling. I don't think we will be able to conclude the model today, but anyway, we can start. And let's have a look. Let's have a look on the more specific look of the diagram, and we are talking now, starting about the shape memory behavior, which is activated by varying the temperature. If we have a look, and you can trust me, obviously, on the basic diagram, that is this diagram here, okay, it has been observed that the shape of the part of the diagram which describe the formation of martensite from MS to MF. Here you do not have 100%, you have percentage divided by 100, that is 1 means 100%. This shape of the transformation of austenite to martensite is essentially the same which can observe for the transformation, I'm talking about geometrically, analytically, of martensite to austenite, that is moving from austenite start to austenite finish. And it has been also observed and validated that this part, transformation of martensite, of austenite to martensite when we cool, and this part, transformation of martensite to austenite when we are giving heat, they can be described, you see here, by a very simple trigonometric function, which is a cos function. And this works, we can write a general expression which has been developed, you see here, in the 90s by two scientists, Liang and Rogers, which can give to us a way to model the transformation by using this very simple trigonometric function, cosine. And one way is to have a look, for example, to the formation of martensite. So start to have a look to this part of the diagram when martensite is going to be formed. The general expression is percent Xi of formed martensite equal to a constant C1, which multiplies the cosine of an angle theta plus another constant, which is C2. then this theta angle, which represent, let me say, the independent variable in this general expression, and which give to us, let me say, the information about the quantity of martensite which is formed, is obviously identifiable by a sort of driving force, which is the difference in the real temperature T minus the martensite finish temperature, because of when, let me say, we do have that the real temperature is equal to the martensite finish temperature, we should have as percent of formed martensite 100%, or that is 1. And so we can express also this general formulation more specifically as Xi equal to the constant C1 for the cosine of the angle, which is defined as F(m) multiplying temperature minus temperature, which is martensite finish, plus the second constant C2. Now, in order to use these expressions, which can allow to us, knowing the value of MF, to answer how much to the question, how much is the percent of martensite when the temperature is T, provided that we know the value of alpha M. In order to use this equation, we now need to define how much is the value of C1 and how much is the value of C2. But this can be easily calculated by applying boundary conditions, because we know that when we are here at MS, that is when Xi is equal to 0, because here we have at MS 100% of martensite, the theta angle of our trigonometric function is equal to pi greco. The second boundary conditions that we can apply is related to the point on MF when Xi is equal to 1, that is, the value of the angle theta is equal to 0. And thus, if we apply these two boundary conditions to the general expression which is written before, we can easily find that C1 is equal to C2, and they are both equal to 1/2. And so if we are going to write the austenite to martensite transformation, you see here in the second red box, we can write that Xi, and this is just and only at the moment led by temperature variation, is equal to 1/2 that multiplies the cosine of alpha m multiplied by the difference T minus MF plus 1/2. Then, if we use these expressions, since we do have Xi equal to 0 when theta, which is defined now in an explicit way as alpha m multiplying T minus MF is equal to pi greco, then we can also say that alpha m, which is in this term, can be defined as pi greco divided by the difference martensite start minus martensite finish. And this is going to work quite well when the temperature is in the range ms to mf, as you can see here in the third red box, because we are modeling the transformation of the austenite to martensite. So we have written a very simple, equations taking into account, and this works, taking into account this general expression by Lyon and Rogers in order to answer to the question that if we are going to start from 100% martensite and we are a temperature value T, which is inside the range MF/MS, how much martensite, which is the percent of martensite that we have formed? Well, we can just use this very simple equation. And if you see here, we find the characteristic temperature, in this case, of the austenite to martensite transformation, MS and MF. Thus, the extreme values of the critical temperature, MS, MF, as well as we will see in a moment, AS and AF, they are also important in order to make a simple, effective, and working model of austenite to martensite transformation. By following the same approach, we can also discuss on what is going to happen when we are giving head to the materials. We are increasing the temperature. So we start, for example, from a material which is 100% martensite, which is going to be transformed to austenite. So not referring to the austenite to martensite transformation, but referring to the martensite to austenite transformation. And just with the same approach, it's quite easy, we obtain, since the general form, we said this one can be applied on cooling and on heating, we obtain that the transformation of martensite to austenite thermally induced, that is induced by a temperature variation, can be written like this. The percent of martensite at a certain defined temperature T is equal to 1/2, which multiplies the cosine of half A, which is defined as the ratio between Pi Greco and the difference AF and AS, multiplying the difference given by the real temperature and the austenite start temperature plus 1/2. And this is the martensite to austenite transformation, which is able to occur when the temperature is in the range austenite start, austenite finish, that is AS to AF. This model works, but it has, let me say, a sort of hypothesis at the basis, because we said that we are going to start, for example, on cooling by something which is 100% austenite, or on heating, we are going to start by a with a materials which is 100% martensite. If we want to make some more general approach, we could also discuss about the possibility that our starting point here, where there is the arrow of my mouse, is not a starting point which, for example, on cooling says to us that the initial conditions are 100% austenite. But generally speaking, and this can be applied in cooling and in heating, let's have a look in cooling, that is austenite to martensite transformation. We could say, let's put us in a general approach in which our starting point at a temperature value, which is T0, time T0, is that we have one pre-existing percent of martensite, which is equal to Xi0. So what has been proved is that if we start from here and we are on cooling, again, the percent of martensite still remains to the initial value Xi0 until we reach the temperature value martensite start. Then for temperature value which are lower than the martensite start, this value Xi0 is going to be increased up to the maximum value, which is Xi equal to 1 when we reach the temperature in cooling martensite finish. And the same applies if we want to generalize during the heating phase, that is the Xi0 value of martensite remains equal to Xi0 till we reach the value of austenite start here, AS. Then the value of Xi0 is going to be decreased, reaching the final value of Xi equal to 0 as figures, as number, when we have reached the austenite finish temperature. Thus, looking to this and now modifying, let me say, the boundary conditions respect to those we have used here with the hypothesis that we are starting from a materials which is 100% austenite, which is then transformed to martensite, and 100% martensite, which is then transformed by heating on austenite. Quite easily, very easily, not quite, very easily, we can say that Xi is equal boundary condition to 1, again, when theta is equal to 0. But Xi, the starting point, is equal to Xi0, that is the initial percent of martensite, when the value of the angle theta is equal to pi greco. And so if we put these boundary conditions, we can define and we can calculate very easily in a general way the value of the constant C1 and C2, which are respectively 1 minus Xi0, the initial percent of martensite divided by 2. C2 is equal to 1 plus Xi0 divided by 2. And so a more general expression of the austenite to martensite transformation is that reported in the last red box, in which just we are going to use C1 and C2 as previously defined, being still the same, the expression for alpha m, okay? And the same for, this applies to austenite to martensite transformation, can be done for the martensite to austenite transformation, that is when we are cooling, we are heating. In this case, the value of C1 by applying the boundary conditions which are reported on this slide is equal again to the value of C2, and they are both equal to the value of Xi0, the original, the starting martensite percent, eventually divided by 100 divided by 2. And so the general expression for modeling of martensite to austenite transformation, when this transformation is is due to the temperature change, in this case heating, is percent of martensite Xi equal to Xi0 divided by 2 multiplying the cosine of alpha A, and again alpha A is the same as we have defined here in the more simple way, multiplying by the difference of temperature, real temperature T minus AS plus 1. Okay, so this is the general, let me say, modeling of the austenite to martensite transformation or martensite to austenite transformation when we are studying the shape memory alloy behavior, which is activated by a temperature change, generally speaking, by using a starting condition in which we have at t equal to 0, that is at the starting point, a defined percent of martensite. Obviously, if this C0 would be or should be or is equal to 0, like in the more simple way, the equation will be those we have defined at the beginning. There is another very interesting thing that we should keep in mind, sorry, which is the basis to make a more general equation, to build a more general equation with which I can anticipate to you we can define a general model able to describe also the superelastic or pseudo-elastic effect, that is the phenomena of stress-induced martensite formation. Let's define this concept, and then we stop, and we will see the modeling in the next lessons. What it has been observed experimentally is that the important, what we have called the characteristic temperature, MF, MS, AS, and AF, they are not invariant with the applied stress. This means that if we apply a stress, the values of MF, MS, AS, and AF for the same materials, for the specified materials, these values are going to change. And they are going to increase when we increase the applied stress. And this increase is quite simple because it is a linear increase. You see here, qualitatively, if we increase the stress, the critical temperature, this is the temperature axis, they linearly increase. And we do have a linear increase, which is characterized by an angle alpha for the temperature, which is referred as MF, and this is the same for the temperature MS, as well as we have a linear increase, which is defined by an angle beta for AS, which is the same for AF. And most of time, alpha and beta, they are comparable. They are very, very near. But nevertheless, in order to maintain theoretically the distinction, let's say that the slope of the variation of the martensite finish and start temperature by increasing a stress, it is defined by the tangent of the angle alpha, and we call it C capital letter M, and the slope of the variation of the increase of the austenite start and finish temperature is characterized by the tangent of the angle beta, which we define as C capital letter A. Having in mind this effect, that is having in mind the fact that we have variations of martensite start and finish, austenite start and finish temperature for the same materials just by increasing stress, we will find a way to include this in the formulation, the general formulation we have seen here, when we have studied only the martensite to austenite, or austenite to martensite transformation, led by temperature change, thus defining a general formulation which allows to us to describe what is going to happen if we change the temperature, or if we, maintaining the temperature at constant value, we apply a stress, that is, we are going to rely on a superelastic or pseudo-elastic effect. Okay, I think that for today it's enough. Next Wednesday, we will continue from this point by seeing the general formulation of the constitutive equations for phase transformation in shape memory alloys. Okay, are there any questions on your side?
Professor, is this PDF available?
Yeah, I will put it now.
Okay. Thank you.
Okay.
Io avrei una domanda, professore.
Pronti.
In questo caso, diciamo, in tutti i grafici che noi abbiamo visto non abbiamo mai nominato il tempo. Dato che queste sono fasi, diciamo, stabili a temperatura diversa, stiamo ragionando assumendo che ogni volta lasciamo abbastanza tempo.
In questo momento sì, dopodiché quando vedremo l'esempio vedremo come quello della molla, come si porta dentro la variabile tempo, ma te lo anticipo, adesso poi lo vedremo in dettaglio, perché bisogna variare la temperatura, quindi io devo avere una relazione che mi dice come varia la temperatura con il tempo, e ovviamente a quel punto le mie equazioni dove ci sono dentro le temperature sono equazioni che riportano come si forma, quanta se ne forma di martensite e austenite al variare del tempo. E dobbiamo fare uno step in più. Se per esempio pensi a un filo metallico, un modo per variare la temperatura è quello di utilizzare l'effetto Joule, e quindi a quel punto con le potenze dissipate per effetto Joule io posso mettere in relazione, in virtù della quantità dell'intensità, densità di corrente che passa, temperatura e tempo, e alla fine ottengo la mia modellizzazione che mi dice Xi in funzione del tempo previsto, che conosco la formulazione della relazione temperatura-tempo.
Perfetto, grazie.
Prego. Any other question? Sorry, I cannot hear very well. Can you repeat slowly, please? Which property are you talking about? Well, at this moment, as I told you, we are not interested in the material strength, and because we are just interested in recover the strain which can be obtained, as we will see in the next lecture, or stresses applied values which are sensibly lower than the material strength. So we do not have to overcome the material strength. And so if you want, generally speaking, we could say that we could apply a sort of rule of mixture for the material properties, depending on the quantity of martensite and austenite which is present inside. But for our purposes, the use of this kind of solution is not for exceeding or designing at material strength, but to design for recovering the maximum strain which is allowable by shape memory behavior. Okay. Any other question? Okay, so I'll put these slides on the Google Drive, and we will see on Wednesday. Bye bye, arrivederci a tutti.
Arrivederci, professore.
Arrivederci.